So this is going to be basically a video recapping the last 3 days. So I know that I've had a lot of people that were absent either due to vacation stuff or that were quarantined or for various other reasons. So I know that chapter 7 can be quite meaty and dense and have a lot of stuff in it at the very beginning for the first chapter. So I'm going to make sort of this Cliff Notes version of the last 3 days. So what I'm focusing on doing here is that this video, will focus on the what to do. It's not going to focus on the why. So this is going to tell you the 3 problem types we went over, how to do them. I'm not going to focus on describing why this works or the rationale behind it. If you want to get that, you can watch the note video that's normally on the YouTube channel and just look at that for the kind of the background details. But if you're just focusing on what the procedure was that we learned last 3 days or what the 3 procedures were, this video is for you essentially. Or if you were there the last 3 days and you forgot some stuff, this will be a good, recap video if you don't want to watch the entire notes video. If I sound a little off, I apologize. For some reason, I'm kind of out of it right now, so this is going to be an interesting video. So if I say weird stuff, then that's why. Not that I don't say weird stuff regularly anyway. So we have p hat, q hat, z or n, and z. So this right here, this first problem, is the main type of problem we worked with these last 3 days. This is being able to take a result from a study or a survey and transform the answer into a confidence interval, which is basically a range estimate as to what's actually going on here. So this pesticide company, they developed a fume that kills roaches. They have a colony of 1,000 roaches, they fill it with the fume, and they find that 850 of them are killed. So we want to figure out, okay, based on that study, about how many roaches, or about what percent of roaches will this fume kill in a colony? Because we could just say, well, 850 out of 1,000, that's the percent. And that might work for some degree, but it's really not the best way of going about it because we have a single numerical guess versus a range of guesses. So if you imagine a jar of jelly beans, and there's a bunch of jelly beans in here, and so many uncountable jelly beans, and I ask you to give me your best guess as to how many jelly beans are in this jar, well, if you give me a single numerical guess, you're probably going to be wrong. But if you say, well, it's between 0 and 20, then you give yourself a little bit better of a chance of being right. So that's what we're doing here. We're taking the single numerical guess and excuse me, we're changing it into a interval guess with some degree of confidence. In this case, 88 or 98% confidence. So how does this work? Well, you need 4 numbers: p hat, q hat, n, and z. P hat is the percent of success from your sample. This is also called the point estimator. So if you hear me say find your point estimator or look at your point estimator or what's your point estimator, that's what I'm talking about, is the percent of success. Point estimator, percent of success, same thing. Right? So in this case here, what we do is we'd simply do 850. That's a bad 8. Let me try it again. 850 over 1,000, which I should be able to do in my head, but like I said, I'm kind of out of it right now, so I'm not going to bother. Actually, I can do that. That's 0.85. Although, like I said, I'm going to check myself here because I want to take any chances of doing this again. There we go. So 0.85. And you do keep it as a decimal for your work, right? 0.85. So 85% is my p hat. Let me make that 8 a little bit better again. Now, q hat is the failure rate. So if I have an 85% success rate, I just have a 1 minus 0.85 or a 15% failure rate. Pretty standard, right? So p hat and q hat, pretty simple to get. Sometimes they'll just outright give you p hat. Like sometimes they'll just say the fume kills 85% of the roaches based on a study. So again, sometimes they figure out yourself, sometimes they just give it to you, but you need your p hat and your q hat first and foremost. Then you need your n. So your n is simply how many tests did you run, how many trials did you do. In this case, we ran it on a test of 1,000 roaches. So my n is 1,000. It's just basically the denominator of this fraction up here. Z is the tricky one. So the z-score is based off of the confidence level. In this case, the confidence level is 98%. Now, if the confidence level, if the confidence level is 90%, 95%, or 99%, the z-score is pretty easy to find that goes with that confidence level, because if you look at your table, it shows you right here that if you have a confidence level of 0.9, 0.95, or 0.99, your critical value, which is what your z is, critical value is just another way of saying the z-score in this problem, is this, this, or this. So it basically automatically tells you what your critical value is if you have one of these common confidence levels, 95% being by far the most common confidence level. Not over here, right? Confidence level, that's what we want to look for. Now, unfortunately, we don't have that. We have 98%, so we have to figure out this z-score on our own. That's one of the reasons why I put this one in here, because this is a little bit trickier. So here's what you do. Your z-score basically represents the cutoff of your boundary. Again, I'm not going to go too much into detail of that. If you want to figure that out, you can watch the notes video in full. So what you do is you take your CL and you figure out the opposite end. So you're going to be 98% confident. Well, what percent doubt do you have then? If you're 98% confident, that means you have a 2% doubt level, yes? Is that one way of thinking about it, right? You're 2% doubtful in your work, right? You're giving yourself a 2% room for error, let's say. Now, here's the thing. You are equally likely to be too far above or too far below the value, right? Usually. And you're equally likely to be too far above or below if you're basing it off of a good statistical research, we'll say. So what you do is you cut this in half and you get 0.01. 0.02 divided by 2 is 0.01. And this is a p-value that you look up in the z-score table. So you're going to find 0.01 or as close to it as you can and find out what z-score goes with that. And that's going to be the z-score we use for our problem. So here's, again, the thing that people often mess up is they forget to divide by 2. And again, it's kind of weird why that is. If you want to know more about why you divide by 2, watch the note video. But essentially, it's just splitting your doubt for low and high. So you don't have all your doubt on one end or the other. You have it split evenly, 1% too high and 1% doubt that it's too small. So once we get 0.01, we would look it up in our z-score table. And we want to get as close to 0.01 as we can. So about right there, I think that's pretty close, 0.0099. That's pretty close to 0.01. So that's going to be a z-score of negative 2.33. Now here's the trick. We actually write it as a positive z-score. So we are going to not write it as negative 2.33. We're going to just simply write it as 2.33 as our critical value. And you'll see why in a second, because when we use the formula, we're going to add or subtract it anyway. So it's just going to be easier to think about it as a positive number. Now we have all our values, so now it's time to use our formula. As I told the class, on your first RPS, I will give you this formula right here. This is for the margin of error. This is your interval range, essentially. Z times the square root of p hat q hat over n. Right? I will give you that formula. Sometimes there's a little alpha divided by 2 down here. Don't worry about that. It's just another fancy way of saying the z-score. Don't worry about if there's another, alpha divided by 2 down here. That's nothing to worry about. But this is the z-score form, or this is the margin of error formula. All you're going to do is take these numbers and plug them into the right spots over here. So you're going to have 2.33 as my z, not negative, but positive 2.33, square root of 0.85, 0.15 over 1,000. Excuse me. So, and then you'd plug that into your calculator to get your margin of error. Because again, your margin of error is going to basically tell you how far above and below your p hat to go, your point estimator to go, to get your interval. So this margin of error is like if you look up a research poll, and they'll often say that, the people that answered yes were 30%. The people that answered no were 70%. And then somewhere on the table, they'll have MOE, usually like plus or minus 5%. That's the margin of error. That's how much room of error they're going to give themselves, essentially. And so that's what we're finding here. This E is basically the margin of error for the typical poll you might see on a news station or something like that. Usually it's somewhere in the bottom of the graph that they display. So next time you watch the news, if you ever do, have a look for that and you'll see it. And so we're going to plug this into our calculator very carefully, by the way. So we would do I'm doing this all in one go because, like I said, I'm out of it already. So the sooner I get this done, the less room I have for error, essentially. So times, now be careful of the parentheses there because this throws people off. Because I want to make sure I don't accidentally just put the 0.85. So I don't want to do this, 0.85 paren. Because right now only the 0.85 is rooted, which is not good. I want this entire thing to be rooted. So if you're going to type it in all in one go, what you would do is you would do a double paren. And do 0.85. Then you would do 0.15. And then you can just slap on the divide by 1,000 at the end with no parentheses. And then you'd cap it off with one last parentheses. So now you have paren. This is the entire square root. And now everything is compartmentalized inside of it. And so then we get a margin of error of 0.026 or 0.03. Do not round it to the first decimal spot. If you're going to round it to the second decimal spot. But we'll keep it as 3 decimals to be super precise, right? So 0.026. That is my margin of error. Okay? Again, pretty short procedure, but there's a lot of numbers you have to search for. Now, how would you write your answer? Because this is not your answer. If I just asked you what the margin of error is, it actually would be your answer. But I'm asking you to make a confidence interval. I want to know what the range of my guess is. So there's two ways to write your answer. The shorthand way is this. You take your point estimator, 0.85. This is like your starting guess. If you had to guess, gun into your head, what percent of roaches would be killed by these fumes? You would guess 85%, because that's what were killed in your sample. That's the only thing you have to go off of. However, you know with 98% confidence that it's going to be 85%, give or take, 0.026. Or put parentheses, it's going to be 85% of roaches dead, give or take 2.6% of roaches. So that's one way of thinking about what this margin of error is. It's a give or take attachment to your initial guess. And the thing about this is that it gives you some confidence in your answer. You can say with 98% certainty that this interval will contain the true value of the amount of roaches this fume will kill. Now, that's the shorthand way of doing it. The confidence, the interval way of writing it, or the inequality way of writing it, they're both the same. And sometimes I will ask you to write it in this way because you're going to need to use those numbers for other things, is this. The format is p hat plus, or sorry, it's one of those days. P hat minus e less than normal p, no hat, less than p hat, God, my p's suck, p hat plus e. So this p with no hat, this is what we're trying to estimate. This represents the actual percent of roaches this fume will kill, right? That represents the truth of the situation. And we are 98% certain that that true percentage, based on this data, is somewhere between 0.85 minus 0.026, less than p, less than 0.85 plus 0 or 0.026. I have to kind of squeeze it in there. My apologies. 85. So you basically take your point estimator and subtract it by your margin of error for the smaller number, and then you take your point estimator and add it to the margin of error for your bigger number. So you would say that with 98% certainty, the amount of roaches, or the percent of roaches rather, that this fume will kill in a colony is somewhere between 82.4% or 0.82 and where's my calculator? 0.85 plus 0.026, 0.876. So somewhere between 82.4% of roaches in a colony and 87.6% of roaches in a colony. So you are 98% certain, based off of this study, assuming everything was done correctly, assuming all the procedures for a legitimate study were followed, based on this study, you are 98% certain that this fume will kill between 82% and 88% of roaches in a colony, if I'm doing some rounding there. So that was the main thing we did in this chapter. That's the main goal, is for me to be able to give you a problem like that and you be able to make a confidence interval from it. Okay? Again, if you want more examples, you can watch the note video itself, but let's get on to the second type of problem. Again, there were three basic problem types. That's the first. Let's get on to the second before I faint here. So the government wants to find out the percent of teens involved in a car crash. They want to use 98.5% for the interval. All right, so what this is asking there is that the government wants to figure out what percent of teens are involved in a car crash. They want a 95% confidence level, okay, and they want to have a margin of error of no more than 5%. So when they run their data, they want to make sure that their E is 5% or less, right? So they want to know how many people do they need to sample so that they'll have an E of less than 5%. Because if they sample too few people, well, that means that their margin of error is going to be too big and it's not going to be as useful. If they sample too many people, that could be costly because usually if you're going to sample or do a research, you have to pay people to do that research. The more they have to research, the more money it's going to cost you. Excuse me. So you want to try to be as close to the exact value as possible, and usually people go a little bit over than the necessary value just to make sure they cover their bases. So they want to go into this figuring out about how many people are we going to need to survey anyway. So what you do is you basically take this E formula, Z root P hat Q hat over N, And you basically solve this for n using your Algebra 2 skills. I do this in the video of the YouTube, the normal note video, so I'm not going to do it here to save some time. But essentially, this gets down to this formula here. N is equal to z squared p hat q hat over e squared. That's how you figure out the number of people you need to sample in a survey to achieve a desired margin of error given a certain confidence interval. Now, here's the thing. Think about this for a second. P hat and Q hat represent the percent of success and failure from your sample. But you haven't even done a sample yet. You need to figure out how many people you need to talk to first before you even get a P hat and a Q hat. So how is this going to work? If you don't know a P hat and a Q hat because you haven't even started the survey yet, how can you use those numbers here? Well, what you do is you substitute in this, 0.25. You basically assume that P hat and Q hat are the maximum possible. And since P hat and Q hat are related to each other, remember one is the success of failure, or one is the percent of failure, one is the percent of success, the most they both can be is 0.5, right? Because if one is more than 0.5, that means one is less than 0.5. But the most they both can be is 0.5, and 0.5 times 0.5 is 0.25. Again, I go over why this is in the YouTube video, so if you want to watch the why part, go for it. But basically, you use this formula if you know P hat and Q hat from past surveys. So sometimes when governments do surveys, they will look at, data from 2 years past and use that P hat and Q hat as a reference point to figure out their N. But if you have no past data to go off of, then you use the 0.25 instead. And so in this case, we don't have any P hat and Q hat to go off of. They don't say, well, based on past data, the percent of teens involved in car crashes 5 years ago was 30%. So we don't know a P hat and Q hat. So we're going to use this guy right here for this problem because, again, we don't have a P hat and a Q hat to use. These formulas I will not give you. You need to memorize them, or once again, just solve this for n using your Algebra 2 skills, and you'll come across this anyway. So in here, we would do n is equal to z. Remember, z is your critical value, or the z-score that goes with your confidence level. In this case, my confidence level is 95%. So I'm going to go to my table. 95% is one of the special ones. So it's right here. 95% has a z-score or critical value of 1.96. Again, critical value, z-score mean the same thing. It's just critical value is the z-score that goes with that confidence. That's why it has a fancy name. So 1.96 squared. Now again, we don't know my p hat and my q hat, so I'm going to sub in a 0.25 because I don't know what they are. And then I'm going to divide it by the desired margin of error, which is 5%. I'm not going to do 5. I'm going to do 0.05 squared because I want that as a decimal. So that's a square, by the way, not a 2. Let me try that again. 0.05 squared. And so then I would plug this into the calculator. So a lot of calculator work, so make sure you don't forget your calculator. 1.96 squared times 0.25 divided by 0.05 squared. You get 384.16. Now here's the thing. If you want a margin of error of no more than 5%, you are much more likely to oversample than to undersample. Because if you undersample, then you might get a margin of error that's more than 5%. You might get a margin of error of 5.5 or 5.4 or 5.3 or something like that. If you oversample, your margin of error is going to be less than 5%, which is usually better because, again, you're more accurate that time. You have to survey more people, but you get a better accuracy, and you make sure you're within your accuracy target. So you always round this number up. Even though it's 0.1, this is going to round up to 385. Because again, I'd rather survey more people than I need than less people. If I survey 384, I might have a margin of error of 5.1% instead of 5%. So this is one of the 2 times in stats, I believe, where we always round up, not as proper math rules, essentially. So that's this problem. Once again, if you don't have a nice z-score, you have to find out what it is using this method down here. It's the same method as before. If I gave you a 96% confidence level, you would say, okay, 96% confident. That means a 4% doubt. So I'm going to cut 4 in half and get 2%. I'm going to look up 0.02 in the table, try to find my CL, or try to find my critical value from there. Again, if you don't remember that, you can just backtrack the video a few minutes and you'll see me do this again. All right, the last type of problem, the easiest one in my opinion. If you have the results of a survey, so it's a 99% confidence level, It's the percent of students involved, or the percent of students that oversleep on weekends, or weekdays rather, is somewhere between 0.56 and 0.64. Again, I'm sorry for my grogginess. Hopefully this is going to come out understandable. I'd rather get this out sooner than later for those that are, again, quarantining and kind of freaking out. So, again, pardon the quality. Hopefully the info is still getting across. So what you would do is you would remember that, well, I'm not going to do the why, I'm just going to do the how, okay? So to find the point estimator, which is p hat, remember p hat and point estimator mean the same thing. You take the biggest number, 0.64, plus the smallest number, 0.56, and then you cut it in half. That's your p hat. If you want to see why that is, again, watch the notes on YouTube, but that's what you do. That's the mechanics. So 0.64 plus 0.56, and then divided by 2, which is basically finding the median, and you get 0.6. So their point estimator was 0.6 or 60%, which basically means that when they took their survey, 60% of students who responded to their survey said that they oversleep on weekdays. This point estimator is what they got from their study exactly, because that sometimes can be hard to see in their interval because it's not clear what they got versus what's in their interval. So this tells you that when they did their study, they got 60%, and then they constructed their interval based off that. The margin of error, the E, is the exact same thing but with subtraction. So you would do 0.64 minus 0.56 divided by 2, and we would get a 0.64 minus 0.56 divided by 2, 0.04, or 4%. So that is their margin of error. And that makes sense because 60% plus 4% is 64%. 60% minus 4% is 56%. So it's pretty clear that that's the correct answer. So that's how you do those. Again, pretty easy. Add and divide by 2, subtract and divide by 2. Make sure you know which is which. Make sure on your RPS quizzes and stuff, you label which one of these is your P hat, which one of these is your E. I do want to know that which one is which. So don't just write down both answers and just leave it. Make sure you mark which one's your P hat and which one's your E, because knowing which one is which is part of the problem. So, like I said, this was a Cliff Notes version, even though it might seem longer than a Cliff Notes. It is the Cliff Notes version of the past 3 days. Hopefully this will help you out. Again, you can watch the full note video if you want the why and the reasoning why some of this works here. But hopefully this will be a nice sort of, like I said, quick, easy access in case you're quarantined, on vacation, or just need a quick refresher. Again, sorry for the grogginess. Hopefully this came out okay. Hopefully somebody's going to watch it so I didn't go through this all for nothing. But I hope you enjoyed the video. Have a good night. Ooh.